So now we understand the ingredients, and we can take these operations, the convolutions and the pooling, and add more of these on top of each other, so we stack more layers. So this is shown in this example here. So we now take the output of the pooling layer. That gives us, it's a 2x2 pooling, so we have only half the number of pixels in each of the spatial dimensions, and then we choose 9 channels, and we then feed that to the next convolutional layers, where we have 16 channels. And if we then go on, we can then take another pooling layer, and then in the end we can take all these 7 times 7 times 16 values we have, and make them into a long vector that we feed into a feed-forward neural network. And in this example, we have only taken gone directly from these features into the 10 class softmax, but we could also add more fully connected hidden layers here. And we train all this by backpropagation as before. And you can see here we give it this 8, and you can see that it has a high probability for the class 8. And you can also see the kind of different filter images that it produces along the way. Yes, so what is going on here? So it's clearly that actually the closer we get to the output, the more we hope that the features we have will look alike if we push images from the same class through. And this is what is illustrated here. So we have taken and looked at the filters and the activations we get if we take a 9 and 2 4s. And you can see, if we look at just the Hamming distance, kind of the pixel-wise distance between the two, so this is what is shown, for example, between the 9 and the middle 4, which is shown in blue. You can see that actually on the data level, so that's the first in the shown in the figure here, you can see that the Euclidean distance is smaller between the 9 and the middle 4 than between the middle 4 and the second 4. And if we then look at the feature representations inside the network, this is actually also true if we look at the output from the first convolutional layer and from the first pooling layer. But then when we get to the second convolutional layer, then we can see that we have actually, now it's the reverse, such that actually now the 2 4s look more the same in this feature representation. This should maybe also be clear if we look at the kind of feature representation in the second row from the top. And then the last one is showing the probabilities for the different classes. You can see it actually now has a high probability for the 9, it has high probability for 9, and also a high probability for 5 and 4. And you can see that for the 2 4s it has highest probability for 4, but then also 9 is pretty high. So these examples have probably been chosen because they're quite similar to a 9. Yes, okay, so another important point, of course, about weight sharing is that we can do some counting both on the number of free parameters, the number of weights in the networks, but also the number of features that we extract in the different layers. So if you look at the convolutional network, right, then we chose to have a 5x5 filter in the first layer, and we have 9 of those filters. Then so that gives us 5 times 5 times 9 parameters. That's a very low number compared to actually what we did with the network we played with last week, and also in the running example from last week. Then if we go to the second layer, we still have these 5x5 by 9 now, because we have a 3D filter. We also filter in the channel direction, and we have 16 of those filters. And then in the last convolutional layer, we have 7 times 7. That's the size of the filter. We have then 16 filters from the previous layer, right? So we have, that's the channel dimension, and then we choose 10 filters. So all in all, this only gives us for the filtering parts and ignoring biases, it gives us only something below 12,000 free parameters. So that's quite low. what is important, of course we had to do a lot of computations, and we can do that efficiently with kind of fast filtering. But what is important here is actually if we look at the amount of signal we have, then the amount of signal we have in the original data, so that's like the features, the raw features, the pixel values is 28 by 28, so that gives us this 784. But then if we look at the amount of features, meaning kind of values we have in the filter maps, the filter images, you can see in the first layer we have still 28 by 28, and then times 9, because we have 9 filters, so that gives us more than 7,000 features in that from the output of that first convolutional layer. And the second convolutional layer gives us, because we did the max pooling, it gives us 14 times 14 times 16 filters, so that gives us more than 3,000. So we have a lot of features to learn from with very few parameters. We can compare this to the MNIST feed-forward neural network example, and there we chose to have 225 hidden units in the first layer and 144 in the second layer, and then of course 10 outputs. So they have been, I think they have been ignored in the calculation from above, but that's still quite a small number. But that gives us more than 210,000 free parameters in that network. So that means that we could actually kind of risk doing overfitting with this kind of network. What is more, maybe even more important, is that if you look at the kind of features we get at each hidden unit, it's a very low number, because that's simply equal to the amount of hidden units we have in that. So that essentially means that there's much less power for the network to actually pick out important features to classify from. So we can say that convolutional neural networks has more signals but less parameters. Yes. So what is the trend now? I talked about that last week, that actually since the kind of breakthrough by the AlexNet, then the performance had gone something like from 15% error in top 5 down to below 5%. So what has happened? And the one trend is definitely that people use smaller poolers and lots of layers. So here we say, in this slide, we say between 10 and 14. This is actually kind of a low number. Researchers from Microsoft have achieved by a specific construction to train networks with up to 150 layers. And the more layers you add, the better performance. So it seems like this hypothesis that deep learning is actually a good way to learn actually holds true in this case. Yes. And also a point here about this image here is, of course, that MNIST is grayscale, but ImageNet is color images. So our input is now 224 times 224. That's the size of the ImageNet images, and then times 3 for the color channels. Yes. And also there's been now a trend in ImageNet competition to actually look for kind of changing the original task a little bit. So it could also be to locate, to not only classify what's in the image, but also say where in the image this class is. So for example, if you have an image with both a cat and a dog, then you should classify it as such and say where is the cat and where is the dog. And you can also use this, use the same kind of ideas for image segmentation, where you want to classify each pixel in the image, and you can do this efficiently with convolutions in order to not perform the same filtering operations again and again. So other applications, of course, is that we can apply this to 1D images. So 1D images could be audio signals, or it could be biological sequences, proteins or DNA. We can also have, in this example, you can see that 1D could also be multi-channel. This is like motion capture, where we put sensors on different parts of the body, and then we have a lot of 1D recordings, or maybe more than 1D if we have all the coordinates. we have audio plus the Fourier transform. Then we actually, as shown in this example, then we go to 2D and brain images. We have a whole image, and we can even like also add a time dimension. Yes, so this is kind of shows many aspects of where we can use this convolutional idea, and I will also talk a little bit about that when we talk about recurrent neural networks, that we can actually put as like a pre-processing step, you can say an adaptive pre-processing step, convolutional filters to extract these kind of features from the image or audio or biological sequence before we send it on to the recurrent neural network. So the last thing I want to share with you is this nice, again, visualization of what goes on in a deep convolutional neural network. So in this case, we have used the famous Google net shown here, which has this very deep net, and the way that Google has been able to train this to be so deep is that you can see they have these kind of yellow boxes with the kind of thing with the text in. That's softmax units. So so part 1 is on the left side hand side, and that is put together with part 2 there. So it's a very deep network, and you have these kind of softmax output where you classify the image in many steps. So you can see in a way that actually the first part should learn already to classify in the first class of softmax classifier, but then we also take the features and pass them on to more convolutional and pooling layers that actually also classify. And this way we can actually make a deeper network that has a better performance. And this video I will play at the lecture, but this is a way to actually again visualize what goes on in a network and do it actually more or less performing art. So what we can do again is we can give some image as an input to the network, and we can choose a specific filter image, and now we can say the kind of features that this filter is sensitive to is like enhanced in the original image. But now we can change the original image to enhance these features even more. And this is what is done in the image. So we start out by the first simple feature filters in the first layers, and then we update our input image 100 times to enhance the feature of one specific filter, and then we move on to the next filter and continue from the image we already had, and then we do that again and again, and we can do that both for the pooling layers and the convolutional, or kind of the output of the pooling layers, the output of the convolutional layers, and then we create images that kind of is enhanced for features that this specific filter is sensitive to. And this creates very exciting, I would say, kind of intriguing and fascinating images on many scales. And it's a nice movie with music, and I'll play that for you at the lecture. You can also watch it yourself following this link here. So that was all I wanted to say today. So here's some references to the different things I've talked about today, and thank you.